In this video, we're going to define and study what are called orthogonal trajectories. So, the idea of an orthogonal trajectory is that when you start with a family of curves, like these blue curves right here, it's sometimes interesting to know what equation might define some curve that is orthogonal to all of these. And the word orthogonal means intersecting at a right angle. So imagine that there is a curve that passes through here, so that every time it passes through one of these guys, it does so at a perfect right angle, a perfect 90-degree angle here. And I was probably kind of off on a couple of these, but you get the idea. There's some curve that passes through and does this. And so if you have an infinite family of curves, like you might get as the solution to a differential equation, for example, we could find, alternatively, the orthogonal trajectory by finding something which is always at a 90-degree angle to it. Another good example of orthogonal trajectories is, imagine the family of curves x squared plus y squared equals r squared. This is a family of curves that we should be fairly familiar with at this point. These are circles centered at the origin with different radii. So these are concentric circles all going around the origin. So we're looking at something like a family of curves like this. Right, like a big bullseye. There's an infinite number of these. I've only drawn 3 of them here. I could easily draw another one, at any point that I wanted to, right in the middle here. You could even draw one even tinier right in the middle there, or right next to one that you've already drawn. All of these are in this family of curves. So what does an orthogonal trajectory look like? Well, an orthogonal trajectory has to intersect each of these curves at a 90-degree angle. So it means that it's passing like straight through them, like this. Passing through all of these curves at a perfect 90-degree angle. Oh, wait a second, that's just a line. If you draw a line that goes through the origin here, which would have equation y equals m times x, this is an orthogonal trajectory. And it doesn't matter what m is equal to, as long as your line passes through the origin, it's going to pass through all of the circles at 90-degree angles. You'll always make these 90-degree angles with every single one of these blue curves here. So these are orthogonal trajectories. And one thing that you might notice also is that the blue lines, the blue curves, I should say, are orthogonal trajectories of the orange lines. If you follow a blue line, it intersects the orange line at 90-degree angles, right? So the blue family of curves, x squared plus y squared plus r squared, are the orthogonal trajectories of the orange curves, and vice versa. It's a reciprocal relationship where, if this one is an orthogonal trajectory of this one, then the same is true in reverse. So how can we mathematically find orthogonal trajectories? Let's take a look at an example. First, we have to start with a family of curves. And the family of curves that I want to start with here is going to be the curves with the form x equals k times y squared, where k can be any real number here. We know what these graphs look like, right? If we just had x equals y squared, we know that's a parabola going through the origin and opening out to the right. And depending on the value of k here, we're going to change the width of that parabola, right? Whether it opens up wider or narrower. And if k happened to be a negative number, we'd actually be opening up to the left. So we're looking at curves that look something like this. This is our family of curves here. Kind of looks like a spider now. There we go. So parabolas which go through the origin here. So what kind of curves are going to be orthogonal to all of these? Well, when we're talking about orthogonality, when we're talking about things meeting at a right angle, what I'm thinking about, what I think back to is, remember this from, if you took it at Highline, Math 91, or else whatever your introductory algebra course was. Think back to to introductory algebra, and when you were finding lines that intersected each other at a 90-degree angle. We called them perpendicular lines at the time. Perpendicular and orthogonal basically mean the same thing, meeting at a 90-degree angle. But for some reason, we don't use the same word in this context. Couldn't tell you why. But the thing about perpendicular lines was that they always had a really important relationship between the two slopes. If you had two slopes, m1 and m2, m1 was equal to the negative reciprocal of m2 in order for those things to be meeting at right angles. If you knew the slope of one, you could find the slope of the other one by taking the negative reciprocal. That way, if you have a very steep slope, a very large number here, 1 over that would be a very small number. And if this one was increasing, this one would be decreasing. So they're going in opposite directions and meeting at 90 degrees. So we're going to use this idea here. If we can find a differential equation that represents this family of functions, we can take the inverse, or we can take the negative reciprocal of that derivative, because the derivative represents the slope, and that will give us a new differential equation for the orthogonal trajectory. Okay, I'm going to erase this just so it's not in our way. There we go. All right, so now I need to take this equation, x equals ky squared, and I need to turn it into a differential equation. And the way that I'm going to do that is actually, rewrite this real quick, a little space. I am going to apply a derivative to both sides of this equation. If I apply d dx to both sides of this equation, it should remain true, right? If an equation is true and you apply the same operator to each side, it's going to remain true. So what happens when I take the derivative with respect to x on the left side? The derivative of x is just 1. And then on the right side, I'm going to need to use the chain rule here. We're going to have 2 times k times y times the derivative of the function y here. So we'll get dy dx. So now, in order to find the dy dx on its own, I'm just going to divide both sides by 2ky. So dy dx is equal to 2ky, 1 over 2ky. Okay, so far so good. The only problem is I have this value k here, and k, as we said before, can represent any arbitrary constant. And so I can't really solve this equation effectively with this value in there. Instead, I'm going to need to find something to substitute in for k. And the good news is that I can actually solve for k in this equation to make that substitution. If I just divide by y squared on both sides here, these guys go away, and I'll have k is equal to x over y squared. So this is equal to 1 over 2 times x over y squared times y. And so now we get some cancellation here, and our final result will be y divided by 2x. So the derivative of y with respect to x is equal to y over 2x. That is the differential equation which describes these blue curves here. If you're interested, you can just solve that differential equation and you'll get right back to what we started with here. Be my guest. All right, so now, this is the derivative. That means it is the slope of these blue lines here. In order to find the slope of the orthogonal trajectory, I'm going to take the negative reciprocal of that result there. So the negative reciprocal, the slope of the orthogonal trajectory, I'm going to do this in orange now to make sure that it's different. For the orthogonal trajectory, we're going to have the equation dy dx equals negative 2x divided by y. Okay, So now that I have this solved, or now that I have this differential equation written here, I want to solve it because my goal is to actually find these orthogonal trajectories, actually find the functions that are orthogonal to this. So this is a separable equation because I can multiply both sides by y to move all of the y's to the left side, and I can multiply both sides by dx to move all of the dx's to the right side. So when we do that, we're going to have the equation y dy equals negative 2x dx. And so now we can apply a derivative on both sides. Or sorry, a derivative, an antiderivative. We can take an antiderivative on both sides. Now on the left, the antiderivative of y is going to be y squared over 2. So we get y squared over 2 equal to the antiderivative of negative 2x is going to be raise the power by 1 and divide by the result there. You're going to get negative x squared. And again, I need a constant of integration, so I'm going to put the constant right here. Now, we could try to solve this equation for y, but in doing that, we'd end up just having a plus or a minus in our answer here. It's actually a little bit nicer to just leave it in this format, or very similar. I can add the x squared to both sides to make this a little more obvious. We're going to have x squared plus y squared over 2 equals a constant c. What shape does that graph make? It's not quite a circle because we have dividing by 2 here. If we just had x squared plus y squared equals c, it would be a circle. But because we have division by 2, this is actually an ellipse. An ellipse which is longer in the y direction than it is in the x direction. And so the curves that are going to be orthogonal are going to be ellipses that look like this. Let's try to get this approximately correct here. Something like that. This is an orthogonal trajectory. Every time it intersects one of these blue curves, it does so at a right angle. All the way around. And so the blue curves are an orthogonal trajectory of the orange curve, and the orange curve is an orthogonal trajectory of the blue curve. You can do this entire process backwards if you're interested for this set of curves. You can do this process in reverse, and x equals ky squared would then be the orthogonal trajectories to this one. We have to go through a differential equation in the middle in order to do this. We got our differential equation, and then we took the negative reciprocal and solved that instead. Okay, so in the next example, we are going to look at another application of differential equations, which is called the mixing problem.